So the second talk this morning is by Ribu Kaul from Kentucky, and he will talk about deconfined criticality by design.
Okay, I want to thank the organizers for inviting me and giving me a chance to speak here. And it's a great honor to speak at Senthil's discussion meeting. Like Joel, I met Senthil first when I just finished grad school. And in fact, I met him the first time in IISc in Bangalore. This was when he was faculty over here. I'd come to visit and see a conference and meet him. And I'd come prepared to talk about what I was working on, and I had written all these notes that I wanted to show Senthil. But then when I went to his office, he told me that, what we'll do is I'll just tell you about my philosophy and outlook in physics. And he didn't really want to see what I was working on. And then we spent the next 2 hours in the small office in Senthil at full volume, brainwashing me into, and that time he was very excited about deconfined criticality. And so, as you'll see, that I didn't realize at that point that 2-hour meeting had a really profound influence on my research, as I'm going to show you today. So I'm going to talk about deconfined criticality, which Senthil mentioned a little bit yesterday. And I have lots of collaborators who I'll mention, but I'd especially like to acknowledge my student, John DeMedio, and UK stands for the University of Kentucky, and Matt Block, who's a postdoc who's now a professor in California State University. Okay, so a lot of the motivation for what I'm going to talk about was actually given by Senthil yesterday. And so I'll refer again and again to his talk, which I hope that many of you saw. And this is roughly the outlook. I'm going to give a so the introduction to the talk is sort of mixed in throughout the talk. There's a very small, very broad introduction right in the beginning, and then very quickly I'll get into technical details. So I apologize, it's not very well organized pedagogically, but if you pay attention, there's a lot of introductory sort of background material, which is on my own work throughout the talk. Okay, so let me begin by talking about, so this, the topic I'm going to talk about is I'm going to talk about Mott insulators and antiferromagnets, and I'm interested in quantum phase transitions in these systems. Okay, so the most simple one which of these Mott insulators, which is very well studied because of its importance to cuprates, is the square lattice quantum antiferromagnet. And if you take the square lattice quantum antiferromagnet, now it's very well known. If you just take the Heisenberg model on the square lattice, its ground state breaks SU2 symmetry in this pattern, which is called the Nail state. So you can divide the sublattice into A and B sublattices, and the Nail state corresponds to the state in which spins on the A sublattice point up and spins on the B sublattice point down. Okay, so early on, there was this idea due to Anderson, which Senthil spoke about yesterday, that there could be non-magnetic states of the system due to quantum fluctuations. And the cartoon that Anderson gave for these is that they are resonating valence bond solids. So the resonating valence bond, I guess a liquid. So resonating valence bonds, I think that's what RVB stands for. And the idea is that you can have singlets between bonds, but these singlets can fluctuate in some way. And the ground state actually is a quantum superposition of all these different singlets. Okay, another simple ground state that you can imagine is a valence bond solid. So a valence bond solid is a ground state where these singlets don't fluctuate, but they form some sort of pattern. And the interesting thing is that on a square lattice, if you make such a pattern, the pattern has to break translational symmetry. Okay, so if you have a static pattern, it has to break translational symmetry. And the simplest pattern you can imagine is this, which is often called the columnar valence bond solid. And you can see that there has to be 4 of these, which in the thermodynamic limit are degenerate. Okay, so this is an example of a broken symmetry state, which is different from the Nail state. And the really interesting idea was sort of pioneered by Senthil and his collaborators in 2004, was that the Nail state and the valence bond solid state, this RVB state, which you might have thought exists between the Nail and valence bond solid state, when you tune some parameter in your Hamiltonian, actually shrinks to a point. So instead of having an extended RVB phase, like people might have originally hypothesized, a very natural situation to go from Nail to valence bond solid is to have this whole phase shrink to a single point. Okay? And then based on lots of developments that have taken place since Anderson's original work, they even suggested what the field theory that would describe this point is. Okay, so this field theory, and I'll talk about how this field theory actually emerges a little bit later in the talk, but right now, let me just say that this field theory, which is the so-called CPN model, so it turns out that if you generalize from SU2 to SUN antiferromagnets, then you still have valence bond solids, but the Néel state breaks SUN symmetry. And then the critical point is actually described by the CPN field theory. Okay, so CPN field theory is a theory of n complex scalar fields all coupled to a U1 gauge field. So it turns out actually that this field theory is actually, even though it's very simple to write down, some of its strong coupling properties are still under debate, and that has made this idea of deconfined criticality somewhat controversial. Okay, so the original idea is very beautiful, and I should say that it's controlled in the large n limit, but it's not known whether, and it's not known how it applies when n is smaller, because it requires you to solve some strong coupling problem for which we don't have any analytic methods. Okay, so to summarize, deconfined quantum criticality is and I'm going to talk about what this is. It's a field theoretic scenario that's very plausible, but it's speculative. Okay, and the reason that it's speculative is because it assumes the existence and stability in the renormalization group sense to certain perturbations of strongly coupled fixed points in gauge theories. And it turns out these perturbations are very complicated. They're not local operators, and I'll talk about what these are later in the talk. But I just want to motivate why we want to study these models numerically and why we want to study this phenomena in concrete numerical models. Okay, and then referring to Senthil's talk yesterday, even if these fixed points exist, so even if they exist in some field theory, there's the question of whether they're emergible. Okay, so the idea, my understanding of what this word means is, so you have some, first of all, we don't even know whether the fixed points exist in the field theory, but even if the fixed points exist in the field theory, the question is whether this whole field theory actually exists and can be realized as, does it emerge in some microscopic model? Okay, so there are tons and tons of gauge theories that you can write down, and they're all different, and as Senthil said yesterday, there is an infinite set of these gauge theories that in principle could appear in some model, and it's interesting to ask whether we have any models for which these can actually happen. And so maybe Senthil can answer this question, and I think maybe he's going to talk about this in one of his lectures. I mean, there is a standard paradigm for quantum criticality, which sort of is a generalization of classical critical phenomena, where you think of a quantum system. So yeah, so maybe that's, I mean, I don't think anyone uses the word quantum, a confined quantum criticality, but one certainly does use the standard theory of Landau-Ginzburg theory of phase transitions for classical critical phenomena and quantum critical phenomena. What I'll show you is that this theory sort of goes beyond the predictions of that. Okay, I'll let Senthil answer this question maybe later in the evening. Since it's not really, since I didn't make up the word, and it's not really relevant to my talk. Okay, so so given the fact that there's this question of both emergibility, and so I want to emphasize that this is different from, so there's a lot of emphasis on realizing the Z2 spin liquid in is finding microscopic models that realize the Z2 spin liquid, and in that case, we know that the Z2 spin liquid phase is really well defined, and we know microscopic models in which we can study them exactly. And then there's a question of just whether it's emergible in specific microscopic models. And I'd like to emphasize over here that in addition to the emergibility, there's also a question of fundamentally, even in the field theoretic sense, whether these fixed points are stable. And so there's an added interest in actually finding microscopic models which realize this scenario. Okay, so now the problem is we need specific models to study this phase transitions, and we want to study them with no approximations. So it's sort of like how when you study Monte Carlo of classical systems, when you study classical critical phenomena, you study with Monte Carlo. And so what we want to do is we want to do the same thing here, but the problem is that we have the sign problem. Okay, so quantum statistical mechanics generally suffers from a sign problem, and this is one of the most serious problems that has prohibited our understanding of quantum critical phenomena. Okay, but luckily for us, there are a few models which we can write down, and basically solving the sign problem is equivalent to finding a way to write the partition function as a sum over configurations with positive weight. Now, luckily, there are some models which are sign problem free. And these are the only examples of models in higher dimensions. So I want to restrict from one dimension where DMRG works very well, in higher dimensions where we can simulate these models in polynomial time. Okay, so now the question is that there are this handful of models that don't have sign problems. Can we find some in which we can study deconfined criticality? Okay, so for a long time, people thought the answer was no, because the simplest, if you take the nail state, the simplest way to go to VBS is to add some frustrated interaction, and we don't know how to solve the sign problem in those models. Okay, so that changed in 2007 when Anders Sandvik, and I'm not going to talk very much about this work because I think Anders might mention a little bit about it on Friday, introduced a so-called JQ model. Okay, and this phase diagram is from some work that I did soon after that, in which he showed that if you take the nail state in the Heisenberg model, if you add this Q interaction, if you make it large enough, you can go to a valence bond solid state. And then you can study the critical phenomena or the phase transition between these two in a lot of detail. Okay, so this was a really pioneering and work that opened up this field and gave us this possibility to really test this emergence of this emergibility and stability of these fixed points in microscopic models. Okay, so I'm not going to really talk about this, but I want to advertise some work that I did where we realized that this interaction that Sandvik introduced is part of a large family of interactions that you can write down. And so the idea is basically if you work in this Marshall basis, what is the most, we all know the Heisenberg model satisfies Marshall sign theorems. If you take its off-diagonal matrix elements, they're all negative in an appropriate basis. It turns out the Q interaction does too. And in fact, this Marshall positivity is is basically required to prove that the model doesn't have a sign problem. So you could ask, in addition to this Q term, are there other interactions you can write down that don't have a sign problem? So Anders discovered this Q method, this Q term, when he was working in this valence bond basis. And the question then was whether you could write other terms that are Marshall positive. And so in this work, it's a sort of eccentric thing because it's not clear what it's useful for. I think it's very interesting to me. But so I found a way in which you can write down all the Marshall positive SU and Hamiltonians in this basis. So it refers to a specific basis, and it may not be all the Marshall, because the fact of a Hamiltonian being Marshall positive refers to a specific basis. But in this particular basis, it allows you to write down all the interactions. And actually, some of them are very non-trivial. I mean, we wouldn't have been able to guess them. Just by looking at them, it's not obvious that they're Marshall positive. So even the Q interaction is not, I mean, now that we understand it, it's kind of obvious. But when you first write it down, it's not obvious at all that it's Marshall positive. And so I won't talk about this, and I don't think it's appropriate for the discussion in the afternoon too, because it's sort of very specific. It's so not of broad interest. But if anyone is interested in talking to me about this, I think it's very interesting that we have this now very large family of models. And we call these designer Hamiltonians, as Senthil mentioned yesterday, because they're not supposed to just be models for any specific experiments, but they're just interesting models which we can solve on a computer very efficiently. So you might be interested in exactly solvable models, not because they describe experiments, but because they're exactly solvable. And so in the same spirit, one is interested in these models because we can solve them exactly on a computer. And in 2 dimension, as I was saying earlier, these are the only models that we know that can be solved either analytically or numerically on large lattices. Okay, so let me show you now, and I'll come back. So now that we have these models, one of the only really good application we've found for them so far is the study of deconfined criticality in SUN magnets. So let me explain, let me go back again to Senthil's picture where you have this nail in VBS and you have this critical point. And now that we have these large set of models which don't have sign problems, we'd like to actually study the phase transition between nail and valence bond solid for every value of n, just not n equal to 2, and understand whether the CPN field theory really emerges at the critical point, whether you have a continuous transition at which both these order parameters go to 0. So I don't know if I said this, and maybe I should emphasize one of the most novel features of the deconfined criticality scenario is that you have 2 order parameters, and both order parameters go to 0 by tuning just one parameter. So when you write down Landau theory, if you wrote a couple Landau theory for 2 order parameters, you have 2 masses, and you might have thought that to make both of them critical, you have to tune 2 parameters. But the whole novelty of deconfined criticality is that you can reach this point where both order parameters are critical by tuning just one parameter. And in addition, as I said earlier, this happens because something beyond Landau theory is going on, and that's described by this sort of field theory, which is the CPN field theory. Okay, so this is a picture from an article we just wrote with Anders and Roger, and I don't again want to go into the details of what these interactions are. Anders will talk maybe a little bit about it, but the idea is that for every value of n of SUN, we can tune between Néel and valence bond solid by tuning some designer couplings. Okay, so these designer couplings are just, as far as the renormalization group is concerned, they are as fundamental as the Heisenberg model, right? They preserve SUN symmetry, they preserve square lattice symmetry, they preserve time reversal symmetry. There are some interactions like the Q interaction and other interactions. And what they allow you to do is for every value of n, they allow you to go from the Néel state to the valence bond solid state at fixed n by tuning a parameter. Okay, and now we have hundreds of ways to cross these phase boundaries. Okay, so I'm just showing you one way which we found useful. And I should emphasize that actually producing a phase diagram like this and studying these critical points takes millions of CPU hours. So in principle, we have hundreds of ways of crossing these phase boundaries. It doesn't mean we've done it in hundreds of ways yet. Okay, so the exciting thing is now that we have these models, we're studying them with basically no approximation. We're using the stochastic series expansion that was pioneered again by Anders. And the only approximation, if you like, is there's a stochastic approximation because you're doing Monte Carlo sampling. And of course, you're studying it on a finite size system. And that's not really an approximation because the system sizes we study are very large. And in fact, in Japan, using a supercomputer, people I think have studied up to 256 by 256 quantum spins. So there are a huge number of spins in these systems. And on all the evidence we've that's many people all over the world, including Kedar and Anders, myself, and Japanese groups, Canadian groups, have studied this phase transition, and there's no clear evidence for first order transition. It seems that both order parameters go to 0 at this point. Okay, so rather than show you all the data for this, I want to show you another aspect. So I remember I said the deconfined criticality, apart from the fact that the order parameters go to 0 at the same point, this interesting thing about it is the emergence of the CPN field theory at the critical point. And so according to this deconfined criticality scenario, if you sit right at the critical point, both Néel and VBS order parameters should be simultaneously quantum critical and should be described by certain scaling dimensions in this field theory. Now, unfortunately, it's not really possible to solve this field theory analytically, except in the larger n limit. And that's one of the nice things. Now that we can study this systematically for larger and larger n, we'd like to understand whether scaling dimensions in these lattice models actually approach those of the CPN theory. Okay, so the Néel order parameter has an anomalous dimension. So this is just a way of parameterizing the scaling dimension, which is standard, which is given by 1 minus 32 divided by pi squared divided by n. Okay, so this is a relatively simple calculation, something even I can do. Calculating the VBS scaling dimension is much more complicated because whereas the Néel operator in the CPN theory is just described as a bilinear of these Z fields, the VBS scaling dimension is described in terms of monopole operators of the gauge field. So I'll come and talk about this a little later in the talk. So if this is unfamiliar to you, I'll sort of explain a little bit about this. But this has been, it's possible to calculate this 1 plus eta in the large n approximation, and it's given by 2 delta 1 times n. Okay, so it was originally done by Murthy, my colleague Ganpati Murthy and Subir Sachdev, and then later redone by Senthil and collaborators using methods by Borokov, Kopustin, and Wu, and they find agreement by very different methods of the computation of this number. So you have these two universal numbers, 32 divided by pi square and 0.1246, and these are very, very non-trivial properties of the CPN field theory at large n. And so the interesting thing is, does this actually emerge in a lattice model? Okay, so by studying these critical points, now at these critical points, we can measure the Néel correlation functions and the VBS correlation functions, and we find they both decay as power laws. And by fitting these power laws, we can extract these exponents, eta v and eta n. So after a lot of computer time and analysis, which I'm not going to show you because I actually want to show you lots of other things, there's this work which we published a few years ago with Anders Sandvik, which shows eta n, and now these are in these models. So for small n, we do it in the JQ model, and for larger n, we do it in something called the J1, J2 model. It doesn't matter. These are all designer models which allow us to reach the critical point and study critical phenomena. And this is eta n. and this is eta v, and the red line is the 1 over n expansion. Okay, so we can even do better than that. We can plot 1 minus eta n times n, and 1 plus eta v divided by n, which allows you to extract these universal numbers, 32 divided by pi square and 0.1246. And if we extrapolate this as 1 over n, it seems to agree very well with the predictions of this large n CPN theory. Okay, so this is very exciting because it shows that you begin with a microscopic model of spins, and as you reach the critical point in the spins, we can actually study some property of this field theory. And the interesting point is that this field theory itself is even though it's a classical theory, because it's a gauge theory, it's very hard to simulate on a computer. And here we can simulate these quantum models very efficiently. Now, I haven't had a chance to tell you what the algorithm, and I probably won't have a chance to tell you what the algorithms are that we use to simulate them, but they're very efficient and built on the idea of the loop algorithm. And so what we can do in these microscopic spin models is we can access properties of this strongly coupled field theory. And I'm going to show you we can actually study some very non-trivial properties of this field theory just after this. But already now we can see an emergence of the scaling dimensions of both Nail and VBS order parameters. And there are lots of good things we see, that we take different designer Hamiltonians, for instance, the JQ model and the J1, J2 model, and they have a consistent trend of the exponents. Now, one of the non-trivial things about the deconfined critical theory is that the Nail anomalous dimension, when n is large, goes to 1. So if you're familiar with ON, Wilson-Fisher fixed point, when you make n large, the anomalous dimension goes to 0. The fact that it goes to 1 has fundamentally to do with the fact that the Nail order parameter is a bilinear in these z's. And this is something that appears very naturally in our spin model. It appears that this exponent seems consistent with 1. And it's also consistent that this VBS scaling dimension becomes infinite. And even the way that they go to 1 and the way that goes to infinity is quantitatively consistent with the large n result. Okay, so we've even actually predicted what the 1 over n square corrections would be if somebody would actually go and compute them. And I think such computations are underway. Okay, so to summarize this part of the talk, I didn't show you a lot of data. I just showed you the results. We have microscopic sign-free models in which we can study the transition between Nail to VBS. And we have very strong evidence that this new kind of phase transition that was proposed by Senthil actually happens. It's a direct continuous transition in which both order parameters are simultaneously critical. And the universality class for this is described by the CPN field theory. And the evidence I showed you for this was these critical indices of eta n and eta v. These computations, I think there were about 3 million CPU hours in total. This was done in Kentucky on a. It's just a cluster. It has I couldn't tell you what the processors were, but I jokingly call it the K computer sometimes. For my Japanese colleagues find that funny because, well, there's a famous K computer in Kobe. But this is just the K computer in Kentucky. Okay, so now an interesting thing. So now that we have models in which we can study this, we want to actually probe many different aspects of it. And one of the interesting things we want to probe is whether this transition is really non-Landau. Okay, so you might be worried that we're just fooling ourselves because there's some model and something we're overlooking. And so we really want to understand this in detail beyond just the fact that we have these square lattice models in which we have this deconfined criticality. So an interesting question you can ask yourself is what happens when you couple 2 layers of antiferromagnets, each of which are going through their deconfined critical points. Okay, so imagine, now I showed you in one layer of a square lattice you have deconfined critical point. On another layer, imagine you have a deconfined critical point. Now what happens to phase transition between Nail and VBS in a bilayer? So the important thing, and again, I'm going to talk more about Berry phases a bit later, but the deconfined criticality scenario really relies on the fact that in a single layer antiferromagnet, there's uncompensated Berry phases of spin half. And one expects, based on the scenario, that if you couple the system in a bilayer, the Berry phases should cancel. And so if you had a Nail and VBS on a bilayer, you should not have a deconfined critical point. And I want to emphasize that this is a very non-Landau aspect of this, because if you just believe Landau theory, the only thing that matters are symmetries of order parameters. And if you consider a Nail and dimensionality, and if you consider a Nail order parameter, whether it's on a bilayer or single layer, it lives in the same dimensions and breaks the same symmetries, and likewise for VBS. So as far as the Landau theory is concerned, the phase transition shouldn't depend on whether you study on a bilayer or on a single layer. Right? It's like studying the Ising model on a square lattice. So triangular lattice, the only difference between the two are irrelevant details. But the fact is, as I'm going to show you, we have good evidence that actually they're profoundly different. So let me show you how I studied this. So I imagine that, I just showed you for SU6 and SU8, I can study the transition between VBS and nail. And imagine now that I have a coupling between the layers and a coupling which tunes it in a single layer. So if I go across a single layer, I have this deconfined critical point, which I've described by this black point. And now imagine I couple both the layers together. Right? So we know if you take two nail states and you couple them weakly, the nail state is stable. If you take two VBS states and you couple them weakly, the VBS state is stable. Same for SU6 and same for SU8. And now we can study this model because it doesn't have a sign problem. We can actually complete the phase diagram. And we can show this VBS state is stable for some region over here, the nail state is region for some region over here. And now we can study the phase transition in this region where the interlayer coupling is finite. Now again, by Landau theory, this transition should be in the same universality class as this transition because it lives in the same dimension, the same symmetries are being broken. And so if you try to write on Landau theory based on that philosophy, you'd conclude that these two transitions are the same. But in fact, we find that when you have finite interlayer coupling, there's very clear evidence for first order transition. And there's double peaked histograms, hysteresis, all the classic signs of first order behavior. Okay, and so this is, to us, very strong evidence that there's something very special about this point where you take a single layer individually, and this has to do with the fact of Berry phases. It's possible that it is possible that there's coexistence, but what we find over here is that it actually is first order. So we study both the stiffness and the VBS order parameter, and we find they go to 0 at the same point. It is possible that they coexist, and we haven't really found models in which that happens yet.
So, is it understood why it goes to a liquid if the interlayer coupling is increased?
Yeah, so actually later in the talk, I'm going to actually talk about the phase transition between nail and valence bond liquid. I want to emphasize that what I call valence bond liquid here is not the exotic spin liquid that Senthil was talking about, but it's a simpler liquid. It is a liquid state. It breaks no symmetry. But in certain situations, the liquid state, its appearance is not as exotic as it needs to be in Senthil's case. So I'll talk about this a little later. But right now, I just want to talk about what happens over here when you cross this phase boundary between VBS and nail. Yeah, so I think actually Anders is going to talk about that on Friday. So I actually prefer to let him talk about it and not repeat. But that's a really good question. So the question is, we have sign problem-free models in which we can study this phase transition. What does this tell us about models that have sign problem, which is phase transition exists? And I think Anders will talk about that. Okay, so now to understand, so we want to understand different properties, this quantum critical point, and this will give me a chance to explain some of Senthil's interesting ideas to you. So first, I'll just recap very quickly what, in one slide, Wilson's idea of a phase transition was. So Wilson's idea of phase transition was that the two fixed points, you have an ordered phase and a disordered phase. And in this phase diagram of infinite space of Hamiltonians, all perturbations about the phases are irrelevant. So if you perturb slightly away, you come back to the phase. But the critical point has one relevant direction. Okay? All the other directions are irrelevant. And the whole idea of universality is based on the fact that whatever microscopic Hamiltonian you create, it only differs from irrelevant details from, which are finally irrelevant from the theory that's described by the critical surface. Okay, and that's exactly the philosophy with which we're studying these models. We believe that models that have no sign problem don't have any extra symmetries. This is the best of our knowledge. And no one knows any extra symmetry that they have. And so we believe that just generic models that allow you to explore the phase diagram of infinite dimensional space of Hamiltonians. Okay, and so here's what I'm showing you. So if you tune some parameter in your Hamiltonian, you make some walk in your multi-dimensional space, infinite dimensional space. And when you cross the critical surface, you go to the critical point, and on either side, you go to two of the phases. So the question is, how does this, so you have this order-disorder situation, and the question is, how does this change in deconfined criticality? How does this flow change? And in fact, it's very important to understand this to explain some of our other numerical work. So the idea of deconfined criticality built on work that was done by Haldane and Reed and Suchdev, and the idea is that if you have a square lattice SU and antiferromagnet, in the long wavelength limit as described by the CPN field theory. Okay, so we all know the SU2 antiferromagnet can be described as an O3 field theory. but you can also write it as a CP1 field theory. And in general, if you have an SUN antiferromagnet, it's described by the CPn-1 field theory. But there's an important detail, is that in this long wavelength theory, there are certain topological defects of the gauge field. I'm sorry, there's a capital L and small a, they're the same thing. This is a gauge field that lives in 3 dimensions, and we know that in 3 dimensions, the topological defects of a gauge field are point monopoles. The important thing is, because of Berry phases, these monopoles have to have a charge of 4. So this was well known originally by Haldane, and then Reed and Sachdev showed that these were related to valence bond solid order. Okay, so if you take a gauge field in 3 dimensions and you take a sphere around it, the flux on the sphere has to be quantized in multiples of 2 pi, so it has to be 2 pi q. The interesting thing is that, of course, generically you could have any kind of monopole, but only monopoles of charge 4 survive the continuum limit because of Berry phases. Okay, so I'm going to call this charge q. It's going to be a very important parameter in what I'm going to talk about in a second. And so now the question is, what is the phase diagram of this field theory where you have the CPN field theory with monopoles of charge 4? Okay, so to understand the phase diagram, again, this is work originally done by, well, actually, this is even older work which was done by Dasgupta and one of his grad students went long ago, and then was taken up by Kamal and Murthy, and I would say really clarified fully by Lessig, Mochunic, and Ashwin Vishwanath in 2003. And what they showed is that if you have, now imagine I have a fugacity for the monopoles, okay, the quadruple monopoles. So my field theory is the CPN theory with quadruple monopoles. Imagine I turn the fugacity of the quadruple monopoles to 0, and I work in this region in which there are no monopoles. So this is described by a CPN field theory with a non-compact gauge field. And what these works showed is that you have an ordered state in this theory, which is like a Higgs phase, which is the Néel phase. And you have a disordered phase in which Z's have a mass and the photon is gapless. And there's a strong coupling fixed point that separates these two, which is described by, this is the CPN field theory for which I was doing the 1/n expansion. It's a very complicated, strongly interacting theory. So the question is, what happens when you turn on quadruple monopoles? Because as shown by Haldane et al., if you take a square lattice SUN antiferromagnet, in addition to this, you always have this perturbation of quadruple monopoles. So what happens to this when you have quadruple monopoles? And this is the scenario that Senthil et al. Proposed, is what happens when you have quadruple monopoles. And they showed that this scenario is very plausible by studying it in various limits. I think it's very convincing, but I should say that for the interesting case where n is 2, 3, or 4, and lambda is 4, we don't actually know that this field theoretic scenario holds, and that's one of the interests of studying these models numerically, in addition to the fact of emergibility. Okay, so now the interesting thing is, once you add monopoles to this theory, this fixed point which describes the photon phase is known to be unstable. Okay, so it's related to the fact that gauge theories which have compact gauge theories are unstable to confinement. And it turns out in this system, the confinement has valence bond solid order. And so what happens is you have this interesting flow where if you tune your parameters in your Hamiltonian across the phase diagram, there's some region where they flow into this red region, which is ordered and is Néel phase. But instead of flowing into the naturally disordered phase in this field theory, once you cross this, you come very close to it, but eventually you go to a valence bond solid. And just at the critical point, this lambda 4 is irrelevant, and you end up in this field theory. So the technical word for this sort of operator is, it's called a dangerously irrelevant operator, because it's irrelevant at the critical point, but in the phase it actually determines the nature of the phase. Okay, so if this was just irrelevant and not dangerously irrelevant, then you would flow into this phase. But the interesting property of this operator is it's dangerously irrelevant, so it's irrelevant at the critical point, and it's almost irrelevant at the phase, but then it actually determines how the system orders. Okay, and so that's how you can get a transition between Néel. So this is part of my introductions on my work. This is the classic work of Senthil from 2004. This is how you can get a phase transition between these two ordered phases, and this is how the this CPN field theory emerges in this lattice model of spins. So what we wanted to ask is, now imagine that you can take any value of n, and imagine you have lambda q. So we will study this field theory with q-fold monopoles, not just 4-fold monopoles, but we let q be any integer. And we'd like to ask whether lambda q is relevant or irrelevant at this fixed point, which is described by this field theory. So again, to have deconfined criticality, not only do you need the existence of this fixed point, but you also require that these monopoles are irrelevant at the fixed point. So this has a long history. So this is a paper which we wrote just later. But I should say the study of this sort of field theory has a long history, starting with Halperin, Lubensky, and Ma, and then taken up again by Dasgupta and Halperin. And there the interest was in studying this with just one component, because it's the field theory of a superconductor. So it's a boson which is condensing, which has a coupled to a U1 gauge field. And so based on this original various limits which were solved analytically, we know, so R is for relevant and I is for irrelevant. We know whether Q-fold monopoles are relevant or irrelevant at the fixed point described by this field theory. So, in this limit, at large n, Halperin, Lubensky, and Ma, and I'll talk about their work hopefully if I have time. And then so this is not on any lattice. This is just a continuum field theory with Q-fold monopoles. Yeah, so if you study it on a square lattice, the appropriate field theory would be Q equal to 4. But as I'll show you, we can study it on different lattices and study different values of Q, and we can actually fill up this whole phase diagram. So at large Q, was studied by various people, Halperin, Lubensky, and Ma. And n equal to 1, there was this very beautiful work by Dasgupta and Halperin, which showed that this field theory is dual to just an XY model. And then these Q-fold monopoles just correspond to a Q-fold magnetic field in the XY model, which has been studied again by various people. And so the relevance and irrelevance of Q-fold monopoles at this fixed point with n equal to 1 is well understood. And at large n, it's known that Q-fold monopoles are always irrelevant. So the question is, what happens now as you go between a large n and a small n? And here you have to actually do some numerical simulation, because you can't study with either duality or large n approximation. It's very hard to study this, because if you take this field theory directly, you have to calculate what happens when you have some very non-local operators. And actually, Lessig, Motrunich, and Vishwanath tried to do this, but it's a very hard problem. Now, the interesting thing with deconfined criticality is that it gives us a natural way to study this by studying systems which are different from square lattices, which have different allowed monopole configurations. Okay, so on the square lattice, we saw Q is equal to 4, and we saw that this insertion is irrelevant, because we infer this because there's a deconfined critical point in this case. And so it's natural to assume that when Q is larger, it remains irrelevant, because we know at large Q it has to be irrelevant. So the only question that remains to fill up this phase diagram is what happens in the case of Q equal to 1, 2, and 3. Because we know at large n they're irrelevant, but at n equal to 1 we know they're relevant. So we should see, as you tune n, a transition from relevance to irrelevance of these monopole insertions. And again, I want to emphasize this is in this field theory, this is not a local operator. So it's not like just measuring some correlation function and seeing how it decays. It's some very non-trivial operator that's inserted into this field theory. Okay, so how does this happen? And so now we can study, based on this work by Haldane and Reed and Sachdev, the monopole charge is related to the minimum VBS degeneracy. So if you take a bilayer, the simplest VBS degeneracy that you can have, I discussed the transition of a fourfold VBS on a bilayer, but you can actually have singly degenerate VBSs, because you can put the states into singlets vertically on a bilayer. And that's what I call this valence bond liquid, to answer your question, Yogesh, earlier. Now, if you take a rectangular system, you have to have a twofold degeneracy, and if you take a honeycomb system, you have to have a threefold degeneracy. Okay, so we can study each of these cases, and we can study nail to VBS transitions. I should say I'm not the only one to study this. It's also studied by Kedar, Damle, and then by this Japanese group. And so this is some work I've shown you on the honeycomb lattice, where we've measured, this is a Binder ratio, which shows a nice crossing. This is n equal to 7. So this is SU7 on a honeycomb lattice. And we can collapse the data very nicely and extract the nail and VBS anomalous dimensions. The cases of n equal to 2 were studied by Pujari, Damle, and Ale, and n equal to 2, 3, and 4 were studied by the Japanese group led by Kawashima and Harada. And it appears that on the honeycomb lattice is very much like the square lattice. So the square lattice we find, so deconfined criticality can only study the phase diagram with n equal to 2 and higher. It can't study n equal to 1. And so it was found to be irrelevant over here, and in this case it's also found to be irrelevant over here. So in some sense it's very similar to the square lattice, despite the fact that for n equal to 1 it's relevant. And so now the interesting question is what happens in the case of Q equal to 1 and Q equal to 2. So as I just was saying earlier, Q equal to 1 is the case where you go from nail to VB, this valence bond liquid, where you have singlets on the vertical dimers. And here we find, again, very good evidence that there's first order transitions, in this case, indicating that single monopoles are always relevant. So while I was writing this up, there was a work by John Chalker's group, which also actually came to the same conclusion using using some kind of classical loop model, which is related in some ways to the models that we're studying, but different. So the most interesting case now is the rectangular case, because what we find in the rectangular case is when n is very small, here's an example for n equal to 3, and q equal to 2 means it's rectangular, we find very clear evidence for first order transition and double peaked histogram. But the interesting thing in the rectangular case is when we make n larger, we find actually that this first order behavior goes away and the transition becomes continuous again. And we can collapse both the Nail and VBS order parameters very nicely at the phase transition. So this allows us now to state when this RG flow of lambda q versus n is stable and when you can get a deconfined critical point. So you can get a deconfined critical point whenever these insertions are irrelevant, and this red box is the region that we have been able to now fill up thanks to the work on designer Hamiltonians. And q equal to 2 in some sense is the most interesting, because in this case we actually see a first order transition for small n, and we see it become continuous for larger n. Now an interesting thing is that if this is really irrelevant, it must be that you get the same critical exponents independent of what lattice you study it when it's irrelevant, because if it's irrelevant, see it flows away here, it flows away here, it flows away here. That's a very good question. So q equal to 1, we've gone up to n equal to 10, and we find a first order transition. So we would like to study the point where it becomes continuous again, but we haven't gone to large enough n. If you take the large n theory and you ask when the single monopole will become transformed from relevant to irrelevant, turns out that that's, if you take that scaling dimension, it happens at n equal to 25. So, that seems consistent with the fact that we're just not able to go up to n equal to 25. Now, right. And so, okay, so as I was saying, if the critical exponents should not depend on what lattice you study them. Of course, this is not the same. This is different from the way in which it doesn't depend on what lattice you study them on a classical model. It's not just because of discretization, but it has to do with the fact that on different lattices in this theory, you put in different perturbations to the CPN field theory, and it's only if those perturbations are irrelevant that you have the same critical phenomena. And here we find that indeed, within our error bars, we have the same critical exponents for square, honeycomb, and rectangular for the Nail and VBS order parameters in the cases in which we find continuous transitions. Yeah. No, we do find no 3 transition. Yeah. So of course, when I say relevant, it doesn't necessarily mean it's a first order transition. It just means that it's relevant at this, so it's different from the CPN fixed point. And in that case, it goes to an O3 fixed point. So actually, an interesting thing is that, so this was very well known, because that's, in my language, that's the bilayer model, and it's well known that if you study the bilayer, you get an O3 transition. The interesting thing is both myself and John Chalker's group find that for n equal to 3, so n equal to 4, there's very clear first order behavior. But for n equal to 3, we don't see any first order behavior. And so it's interesting that there might be a transition which is not the NCCP2 field theory, but another one like the O3 transition, which we have critical exponents for. Okay, so now I want to discuss, at the time when deconfined criticality was proposed, there was this other idea of an easy plane deconfined critical point, and this is something that we've revisited and where we find first order transition. So I'd like to tell you about that. So imagine you have the quantum XY model. So in some sense, we've taken the CPN field theory and we've studied perturbations which have to exist in SUN antiferromagnets, which are these monopole insertions. But you could try and reduce the symmetry of the SUN to some lower symmetry and ask, and this reduction of symmetry we know is relevant at the fixed point, and what we want to ask is whether you get new fixed points with this theory. So imagine you take the quantum XY model. So the XY model, has a U1, let me call it, there's a rotation symmetry. There's a U1 rotation symmetry, and there's a Z2 symmetry if you apply no magnetic field. Okay, so the question you can ask now is, what is the nature of the transition from superfluid to VBS? So this was actually done even before deconfined criticality, and may have been one of the things that inspired deconfined criticality by Anders Sandvik and collaborators. And what they showed is that you can add a 4-spin interaction. In fact, this is like one of the first designer, depends what you mean by designer Hamiltonians, but at least for Monte Carlo, this was the first very clever idea of introducing a 4-spin interaction with no sign problem. And what they showed is when k is large, the superfluid, which we all know exists in this model, is destroyed and goes to 0, and the VBS order parameter increases. Okay, so this seems to happen in a very continuous way, which suggests that this might be the simplest example, or the first example in 2002 of a deconfined critical point. And then Senthil et al. Developed a field theory for this phase transition, which would describe the nature of this transition if it was continuous. Okay, then since Sandvik and Melko revisited this, and they found that even though they don't see any evidence, clear evidence for first order behavior, there's some unusual scaling. Okay, and I don't want to go into details of why this scaling is unusual, but people started suspecting that this transition could be first order, even though no one had actually seen clear evidence for first order behavior. Okay, so now given the success we had for the SUN case of generalizing from SU2 to SUN, I got interested with my grad student John DeMedio in trying to do this for the easy plane case. So I want to extend the easy plane case to SUN. So let me follow Affleck's recipe, which says that if you take a SU2 antiferromagnet, you can generalize to SUN by, for SU2, T star and T are the same, up to a sign. Well, T star and C are with the conjugate and fundamental representation are the same. And so you can write the Heisenberg model in this form, but in this form, it's very easy to generalize it to large N. And the salient feature of this generalization is that you can have two-side singlets for any value of N. So if you put all the spins in the fundamental representation, you need N sides to form a singlet. But if you put them in fundamental conjugate, then you can form two-side singlets. So now our idea, DeMedio, John, my grad student, my idea was that we'll reduce this SUN symmetry. Now SUN we know has N square minus 1 generators. There are N minus 1 of them are diagonal, N square minus 1 are off diagonal. So let's think of the XY model as the Heisenberg model, but a model in which you only sum over the off diagonal generators. Okay, so then you can rewrite and find a model which is the analog generalized to larger N. So it doesn't have SUN symmetry. It actually has a lower symmetry, which is a U1 to N minus 1 cross Sn, where Sn is, so this symmetry is very easy to understand. It has to do with the fact that you have N colors of bosons. Each of the boson colors are conserved, and all the bosons are identical to each other. And that's the origin of the symmetry. So now we want to study the phase transition between, and the good thing about this model, again, is that it can form a VBS because it can form two-side singlets. And we can study now this model as a function of N. For small n, we find that it's superfluid. And for large N, we find the superfluidity goes to 0 and the VBS order parameter turns on. And now we can introduce a Q, so we call this J-perp because it's different from the Heisenberg model. But we can add a Q-perp term to this J-perp, and we can study now at a fixed value of N the transition from superfluid to VBS as a function of N. And here are some quantities which cross. And it seems very nice that the superfluid and the VBS order parameter, this shows where it goes to 0 as a function of 1 over L. They both seem to go to 0 at 1 over L at the same place. Okay, and then we can do this for SU5, and now we can do this for any value of N. We can write down a phase diagram which shows the transition with superfluid and VBS for this model as a function of N. And here are the order parameters. This is the stiffness, and this is the VBS order parameter shown for N equal to 2. And now if we take this point in the middle, close to where we find a phase transition, we see very clear evidence for first order behavior. Okay, so for small l, both Nail and VBS, and I want to emphasize that we've searched very hard and looked for this in the full SUN symmetric case and never found it, that you have these magnetic and VBS order parameters fluctuating, but when you make it larger, you see the system switches between being Nail and VBS, and as you make the system size even larger, the tunneling time between those two increases, indicating that this is a first order transition. And we can make histograms for both Nail and VBS order parameter, and we see classic double peak structure which grows as you increase the system size. And if you do hysteresis, you can actually see that there's nice hysteretic behavior in this phase transition which increases as you increase the system size. So it appears this transition is first order. One could try and ask why it's first order and whether it will remain first order when N is very large. And maybe I don't have time to discuss this. I can discuss this later. But basically, the point is that the field theory that describes the transition, the symmetric case, is described by this Halprin-Lubensky-Mao model. And Halprin-Lubensky-Mao, there's a phase diagram. So there are three parameters. There's R, E, and U. And so if you tune the critical surface, you can study the phase diagram in the EU plane. And there are 4 fixed points. 3 of these fixed points have a relevant direction in addition to R, so don't describe critical phenomena. The CPN field theory has all directions irrelevant except for R. Now, you require N to be larger than 183 for this flow diagram to hold, but one believes that this holds all the way up to n equal 2. I don't have time. This is one of Senthil's important contributions in the deconfined criticality scenario, was he made it believable that this actually holds down for smaller n. So now you could ask, with the easy plane model, you can do a similar analysis. So you take the field theory, and now in order to preserve this U1 n minus 1 cross Sn symmetry, you have to add a term which looks like this. So this doesn't have SUN symmetry, but it does conserve each of the bosons. Now you might have thought the n U1s, but of course the Z is charged, so one of those U1s is gauged, and then you have all of them equivalent, and so you have an Sn symmetry. And so you can calculate the beta functions now. And so there's R, U, and V. And actually it turns out now that the fixed point that you're interested in, which you want with E square U and V not equal to 0, only happens for n larger than 5,300. Now these estimates are known to be unreliable, but this may be one reason why at n equal to 2 and n equal to 5 we see first order behavior, but we're not sure yet. Okay, well, I have 2 minutes more, and maybe I want to just talk a little bit about this last thing and just tell you very, very quickly about it. I probably won't have enough time. I'll just introduce some new models that we're studying, which have quantum criticality, which go beyond the Landau, Ginzburg, Wilson, Senthil paradigm. Okay, so these models are, I was just joking. The models are, so we saw on the SUN model can be written as T times T star. And this T times T star can be thought of as a singlet projector. Okay, so you can rewrite this as a projector onto singlets, where the singlets are the sum over equal colors on neighboring sides. And the reason they have SUN symmetry, of course, is because you can multiply the singlet by U and U star, and that leaves a singlet invariant. So of course, the projector is also invariant on that symmetry. So I got interested in the idea that we can study this actually on non-bipartite lattices. If I forget about SUN symmetry and I just think of the singlets as the fundamental objects. So imagine I have a triangular lattice, and on each lattice I have n colors. And now I project onto a singlet state between these two colors. I'll call this a singlet. It's not an SUN singlet. It turns out it's an ON singlet, because I can do, so there's no two sublattices on a triangular lattice, but I can multiply all the sides by uniform ON symmetry, which leaves the Hamiltonian invariant. And I can ask now what the phase diagram and critical points in this model are. And it turns out that they're not described by deconfined criticality. They have a different field theory that describes them. And this is something I'm studying right now. And I don't know if I have enough time to tell you. But let me just give you a gist of what I think I have. So let me first tell you this. These models are not, although they may seem crazy, they're not that crazy. They're actually related to models that we know. For example, n equal to 2, they map to an XXZ model that's been studied by various people, some of them who are over here. For n equal to 3, it maps to a spin 1 biquadratic model. So this is interesting. If you take the spin 1 biquadratic model on a triangular lattice, it has no sign problem. And you can study the properties of the ferrospin nematic ground state it has on very large lattices, something I did just a few years ago. And the interesting thing is when you make n very large, they map to a quantum dimer model on the triangular lattice, or on whatever lattice you're studying it. So it maps to a quantum dimer model with only an off-diagonal dimer interaction. And this was something that was studied by Mosner and Sondhi in 2001, and is known to be VBS ordered. Now the interesting thing is it has a very complicated VBS order, and at small n we see that we have this kind of nematic order. And now there's an interesting question of what the phase transition between these two are, between the nematic and the VBS order, and they're not believed to be described by deconfined criticality. And one could hope maybe that this is a situation where finally the Anderson RVB is not just a single point, but becomes a phase. Okay, so in the interest of time, I'll skip over my data, and we studied various models, and we have some evidence actually that what happens in this case is unlike the case on bipartite lattice where you go continuously between nail and VBS, there's actually some region in which there's an RVB phase. And again, to refer to Senthil's talk, this is exciting because it's going to allow us to study critical phenomena between short-range entanglement and long-range entanglement phases. Okay, so the deconfined criticality was a special case where you had LRO and LRO prime, both with short-range entanglement at one critical point. But here you have a phase, so you have these new critical phenomena that you can study, which are poorly understood, and we're just beginning to understand, and something we'll study. So that I can finish on time, let me just give you an outlook here. So I mentioned briefly that we have these new set of models, which are SUN symmetric, which don't have the sign problem. And and we found two kinds of ground states in them, nail and VBS. And we can study the critical phenomena to death now in these models because they don't have a sign problem. And we have almost a complete classification in 2 dimension of what kind of critical phenomena you can have with these systems on bipartite lattices. Okay, and now we have some questions which I don't know the answers to. Can we realize new spin liquids or phase transitions in these models? So if we can realize spin liquids, it's very exciting because we'll be able to study critical phenomena between the spin liquids. Again, something Senthil is going to talk about either today or tomorrow maybe. And we have this large space of models which we can study without a sign problem. And the question is, are some phases too exotic to realize in these models? And we don't really understand how to find phases, new phases in this model, except for trying to simulate them, which of course is very difficult. Okay, then one important application of these models was to deconfine criticality. And here in the SUN case, we have very nice evidence that this deconfined field theory exists. And I want to contrast it to the easy plane case where there's clear evidence for first order and strange scaling behavior. And I showed you how we can have a continuous transition with large n exponents which agree with 1 over n expansions. And we have this nice phase diagram which classifies all bipartite deconfined criticality in 2 dimensions. Okay, and then finally, I didn't really have time to tell you, but we can study analogs of these models on non-bipartite lattices. I just started studying on the triangular lattice, but we could study on the Kagome, we could study in the pyroclaw in 3 dimensions. And there's a question of what kind of quantum spin liquids exist. And of course, the thing which I'm most excited about also is not just the quantum spin liquids, but how they're separated, what kind of phase transitions are separated from ordinary phases. Okay, so with that, I'll thank you for your attention.
Thanks for finishing on time, even though there were lots of questions. But we have time for maybe a few quick ones more. Okay.
May I request you to? May I request you to go back to this Outlook 2 slide, number 2. Yeah, I mean, in this plot and also in the other plots where you showed data for JQ, I notice always that the exchange strength is rather small compared to the Q term, whereas the 2 states on both sides of the transition are rather different. I mean, do you have some explanation for why is it that such a small exchange strength can drive a transition between states that are so different?
Yeah, in some sense, so since I'm not really studying, how do I say, I guess since I'm really interested in, I'm just trying to come to the phase diagram which I showed you. Okay, here. So, so there's an energetic question of why Q over J, the Q interaction likes to send neighboring sites into singlets. Okay, so you might guess that it favors VBS order. But if you just take spins and you take the Q interaction, you put it in the classical limit, the ground state is still the nail state. So it's not absolutely clear to me how this number 24 arises. It's sort of a non-universal number that depends on the details. Now, I do want to emphasize that if you study for different n, this Q parameter can actually become very small, actually become 0 once you cross n equal to 5. And even if you're interested in the SU2 case, there's work by Anders and then also Kedar and other people which have studied 6-spin interactions. And with the 6-spin interactions, it turns out that this number reduces from 24 to some number of order 1. So I don't have any insight in, like if you showed me the JQ model, I would not, and I think people have tried to compute this number 24 by mean field theories and various other methods, and I'm not an expert at that. My understanding is that that generally doesn't work. So I don't think we have any understanding of why it is. But I want to emphasize that to study critical phenomena, the fact of this number being whatever it is not relevant as long as we can access it at some finite value of Q. I don't know if that answers your question. Yeah, we can talk about it more.
Yes.
I don't think
Okay.
so. In your table of Q and N relevant and irrelevant, for Q equals 2, you see that it goes from first order to continuous. But is it really clear cut where that happens, or is there some? Is there a borderline case that it has some strong corrections to scaling?
Oh yeah, that's a good question. So n equal to 3. So I mean, clearly when it's relevant so as Senthil was pointing out in this case, relevant doesn't always mean that it's first order. It may also be continuous. But in this case, it happens to be first order. And when it's first order, it's very clear it's first order. You just have to make the system size bigger. Now what happens is that the system size has to get bigger and bigger and bigger before you start seeing first order behavior as you make n larger. And at this point, you don't see first order behavior even on the largest lattices that we study.
But you're really confident that n equals 4 is continuous.
Well, I'm not confident about anything, but
Scaling that we see before.
yeah, no, we do see corrections to scaling. So maybe a question is whether you see. Yeah, I don't know how to quantify the corrections to scaling, but I'm not sure whether it has less corrections to scaling than the case of q equal to 4. Yeah, it's a good question.
I think, oh, okay. One last one.
Recall this calculation by Harada and Kawashima, which
Yeah.
said that that's second order conversion.
Yeah.
Just limited data.
So I asked this. I met Kenji Harada in Singapore, and he's a quiet person. But I asked him, and he did tell me he did say that he thought that maybe they hadn't gone to big enough system size at that point. So if you see the data over here, we have to go to pretty big system size before we see the first order behavior. Like if you just had small system sizes, it looks somewhat continuous, right? And you have to go to big system sizes to see its first order. So he felt like maybe we didn't have. And so as Anders says, it could be that we have the same problem on a bigger scale for some value of n. But it's hard to believe if it's becoming more and more continuous that it just doesn't happen at some finite value of n. I mean, the criticism could be that it just happens at n equal to infinity, it just keeps getting weaker and weaker. And that's possible, but the other reason we don't think that happens is the critical exponents seem to agree with the ones we find in the square lattice.
Any other questions? If not, we'll thank the speaker again and break for coffee. And we resume at 11:30.